Hello students, welcome to today's lecture. Today we are going to discuss the mechanics of particle motion. What happens if particle is moving through a fluid? Okay, so how it will move? Okay, what is the velocity profile? How the velocity will change? Okay, or how the particle will accelerate? Okay, we will derive the motion of that particle. Okay, so if the particle is moving through fluid, so let's say we have a fluid. This fluid can be anything. It can be air or water or any other liquid. Okay. So if the particle is moving through the fluid, then what will happen? So there will be some drag force, right? As we discussed earlier. So this particle will experience some drag. So let's say this particle is moving inside the fluid. So the particle is now inside the fluid. It is moving. So it will experience a drag force in the opposite direction, right? Drag force. Okay. Similarly, it will oppose by the buoyant force, right? You know buoyant force. Buoyant force, right? So if the particle moves in the downward direction in the fluid, so it will experience two forces. One is drag force, another is buoyant force due to the fluid. Okay, you already know Archimedes principle. There, the buoyant force is discussed. So if the particle is moving in this direction, so it will experience buoyant force and drag force in the opposite direction. Okay, if the particle is moving in this direction, then it will experience drag force in direction and the buoyant force in direction, right? Okay, so now how to calculate the velocity or acceleration? Okay, so let's calculate that. Now the particle can move, or the particle is falling only because of some external force. So the most common external force is gravity, right? Because of the gravity, this particle is falling down. Okay. Second is there can be centrifugal force. Suppose this particle, centrifuge. Okay, in centrifuge the particles are rotated, right? So as you know, if the particle is rotated, then it will try to move outwards, right? Because of the centrifugal force, and centrifugal force will act downward, right? So the particle will try to move away from the center if it is rotating with, let's say, angular velocity. So in that case also, while the particle is moving in this direction, suppose the particle is rotated by a centrifuge, and we have a fluid here. Okay, the fluid will also rotate. This particle will, because of the centrifugal force, this particle will move outwards, right? So now same, the particle will experience drag force in this direction and buoyant force in this direction, right? And particle is moving in this direction because of the centrifugal force. Okay, so we call that force as external force external. Okay, so we'll discuss the motion of the particle due to these two external forces. Okay, so we'll derive so the particle is moving in this direction. Let's say this particle is inside a fluid and moving. Okay, definitely. So it is fluid. It can be any liquid or gas. So this particle is moving downward because of the gravity. So this is the external force because of which the particle is moving downwards. Okay. So what will be the external force? It's nothing but mg, right? This mass is the mass of this particle. Okay. What about the opposing forces? We'll have drag force, and we'll denote the drag force by Fd, right, in the opposite direction, and we'll denote the buoyant force by Fb. Okay. Now particle is still moving, so that means you know from Newton's law, right? So if particle is moving, so the acceleration is equal to net force, right? Net force. So what is the net force there? So if you take external force as the main, so the particle is moving in this direction, right? Resultant movement is in this direction. So this Fe must be higher. So Fe first, external force, minus buoyant force in the opposite direction, minus drag force, right? This is your net force acting on the particle, right? So because of the net force, the particle will accelerate, right? You know the Newton's second law, m is equal to ma. So if there is a net external force, the particle will be in acceleration. So you can write d. Let's write du by dt. The u is the velocity of the particle, m is the mass of the particle, this particle. Okay, so this is nothing but du by dt is nothing but acceleration, right? So if the net force is 0, then there will be no particle motion, there will be no acceleration, or there will be no acceleration, but the particle can move with constant velocity. Okay, no acceleration means no velocity change, right? So if the velocity is constant throughout the motion, then the acceleration will be 0. Okay, that's what is called terminal velocity. If the acceleration is 0, then the particle is moving with constant velocity. That is called terminal velocity. Okay, we'll discuss that. Okay, now, so we have done the balance, right? Force balance, right? So you can see in this also we have done the force balance. This is external force minus buoyant force minus drag force, right? And forget about this GC. It is just a constant. In SI unit, the constant value is 1. So m du by dt. Okay. Now calculate each term. So what is the Fe? This is external force. That is, in this case, first we are considering gravity. It can be any centrifugal force as well. So I will write MAE. Okay. So force due to external force is nothing but mass of the particle into the acceleration due to the external force, right? So this acceleration can be anything. It can be due to the gravity. If this gravity, you can simply write mg. If this is because of centrifugal force, you can write omega square r. Okay, we'll come to that part. So for simplicity, we'll derive the general equation. So this is mass into acceleration due to external force, MAE. So what about the buoyant force? So in Archimedes principle, what does it say? The Archimedes principle says that if the particle displaces some volume, right? So that the mass of the volume of that volume of the fluid will exert some external force, right? So how to calculate that? So so this is the particle. It is moving through fluid. What is the particle mass? M. What is the density of the particle? Rho p. So this particle displays a volume, right? What is the volume? M by rho p, right? This will be the volume displaced by the particle. Now, what will be the mass of that mass of the fluid of this volume? So the mass of the fluid displaced will be equal to what? Density of the fluid, that is rho. Let's write rho is a density of the fluid, not particle. Density of the fluid into the volume, right? What is the volume? Volume is just calculated m by rho p, right? So this is the mass of the fluid displaced. This mass of the fluid will exert force, right? So what will be the acceleration? A, right? Because the particle is moving in this direction with acceleration AE. So the force due to buoyant force will be m into AE. Then what is this m? M is the mass of the fluid displaced by the particle. Okay. So this is the mass of the fluid displaced. So you just calculated the mass of the fluid displaced. So that is nothing but rho of the fluid into what is the volume of the fluid displaced? That was m by rho particle, right, into ax external acceleration. Okay. What is the drag force? What is the definition of drag force? So from the definition of the drag coefficient, what was the drag coefficient first? Right, the drag coefficient CD equal to FD by projected area by rho U square by 2, right? So if you rearrange, you will get FD equal to, you can rearrange that. So if you rearrange, you will get this. Okay, ignore GC. GC is a 1 in SI unit. If you are calculating SI unit, just put GC is equal to 1. So you can get FD. FD is here again calculated. Again ignore GC. So we have found. Now just substitute in that previous equation. So what was that? M du by dt. Remember, m is the mass of the particle. Okay, so and m AE, right? It is F external force. Then buoyant force. What is buoyant force? Just calculated m rho AE by rho density of the particle. This is density of the fluid. And again the drag force. That is nothing but CD U square rho A P projected area by 2m. Right, just simplify this, then you will get this equation, right? Now, so A is nothing but just external acceleration. The external force can be anything, right? As I told you, we have two common external forces. One is gravitational force and another is centrifugal force, right? So just simply put according to the force you have selected. Okay, so this equation is there. Okay, so if there is a gravity, then what is the acceleration due to gravity? That is g, right? So you have to simply put g, because the external force is gravitational force, so acceleration due to gravitational force will be g, right? So if you put g and simplify, so you will get this, right? Now if the external force is centrifugal force, then you know this is omega is angular velocity, right? So if you want to convert into linear velocity, then into omega r. But what is acceleration? It is omega square r. Okay, this is not angular acceleration, this is linear acceleration in this outward direction. So it is omega square r. So instead of putting A is equal to g, you have put g in case of gravitational force. Now we are in centrifugal field, so we have to put A is equal to omega square r. So if you put in this equation A is equal to omega square, you will get this. Okay, so you can check the angular velocity. Omega is nothing but radian per second. R is the radius of the path of the particle. Okay, so you'll get this equation. So this is the uh, force balance equation for gravity and centrifugal force. Now we are mainly interested in terminal velocity, right? So if the particle is moving through the fluid under some external force, what will be the terminal velocity? Terminal velocity means the constant velocity of that particle in that fluid. Okay. So now terminal velocity is defined as the what is terminal velocity basically. So if there is no acceleration, right? If there is no acceleration, that is du by dt will be 0, then what will be the velocity? That is called the terminal velocity. So the actually the velocity terminal velocity is the velocity. It's a maximum velocity actually the particle can attain inside the fluid. Okay, so you can read out here. So how to find the terminal velocity? So simply put this term equal to 0. Du by dt is equal to 0 in this case also. So du by dt means there is no acceleration. There is no net acceleration. Okay. So if you put this term equal to 0, then you will get the terminal velocity for both the cases, for gravitational force and for the centrifugal force. Okay. So if you put 0 here and rearrange, you can find u. Then we'll move to the next page. Okay. So if you rearrange and write u equal to ut, because the acceleration is 0, now the velocity is nothing but terminal velocity. Then you rearrange, you will get this. Okay. This is for gravity. And if you rearrange the centrifugal equation, then you will get this terminal velocity in the centrifugal field, and this is in the gravity field. Okay. Now you can check here. This rho p is nothing but density of the particle. Rho is the density of the fluid. M is the mass of the particle. AP is the projected area of the particle. So if it is a spherical particle, what is the projected area? It is nothing but the circle, right? If the diameter of the particle is dp, then what is the projected area? It is a circular area, right, with diameter dp. So pi dp square by 4. This is CD is drag coefficient. This is the density of the particle. Rho is the density of the fluid. Similarly here, this omega is angular velocity and rest are the same. Okay. So if you have a particle, generally the particles are of spherical particle shape. Okay. So if you want to calculate what will be the terminal velocity of a spherical particle, just plug in the AP is equal to projected area pi dp square by 4. Rest are same, and just rearrange again here. Just put the projected area as pi dp square by 4. You'll get. Now the drag coefficient, as we discussed earlier, drag coefficient CD was a function of Reynolds number, right? We already discussed in the previous class. So if you see this figure, you can see on the x-axis we have Reynolds number, and here we have drag coefficient, right? So it changes, right? As I told you, if the Reynolds number is less than 0.1, then it is Stokes regime, right? Stokes regime. And if it is higher than 1, then it is Newton's regime. So you can find out the range. So suppose you first to calculate the CD, first calculate the Reynolds number. So first calculate Reynolds number, then draw vertical line. You can get the drag coefficient. Okay. So this is how you calculate the terminal velocity for a spherical particle in gravitational field as well as centrifugal field. Okay. So there are two kinds of settling regime. Settling regime in the sense how the particle is settling through the fluid. Okay. So free settling. There is one called free settling, and another is hindered settling. As the name suggests, free settling means there is no obstacle to the particle. Suppose this particle is moving through the fluid and it is away from the wall. Let's say this is wall. So it can easily settle through down, right? Because of the external force. So there is no hindrance from this wall or any other particle. Let's say we have a lot of particles here in case of suspensions, but the distance between these two particles are so large that it does not affect the motion of the particle. So this is called the free settling. Okay. Another is hinder settling. Suppose the particle is very large and it is close to wall, then it will be offered some resistance by the wall, right? So it is kind of hindered settling. And again, if the particles, there is suspension, they are very close, the particles are very close to each other, then what will happen? It will collide with each other, right? It will follow some kind of Brownian motion. Then also it is called hindered settling. So how to calculate terminal velocity for hindered settling? Will read in the future. Future means after this next class. Okay. So this is the two kind of settling regime: free settling and the hindered settling. Okay. Now we already derived the general form of the terminal velocity for any particle, right, under gravitational field and the centrifugal field. Now assume that the particle is spherical, right, of some diameter dp diameter. So you can calculate the mass, right? If the density of the particle is rho p, then what will be the mass of the particle, the spherical particle? So it is nothing but volume into density of the particle, right? What is the volume of the particle of diameter dp? So it is nothing but 4 by 3 pi r cube. In terms of diameter, it is nothing but pi d cube by 6. Okay, so this is the mass of the particle. What is the projected area? As I told you, for a spherical particle, the projected area is nothing but the circle of diameter dp, right? So it is same. If you put this two values in the previous equation, right? So for gravity settling, this was the equation. So just put it and rearrange or simplify, you'll get this. This is the terminal velocity for a spherical particle under the gravitational force. Okay. Again, CD can be calculated from Reynolds number. So I'll show you in a while. Okay, so this is the terminal velocity of a spherical particle of density rho p, which is moving inside a fluid of density rho, right? Okay, so what about the centrifugal one? So simply you can put these values in the centrifugal equation also. So from now onwards, I will just simply take the gravitational field only. Okay. However, if you can calculate the same thing for the centrifugal field, just put these values. Okay. Now I have shown you two flow regime, not settling regime. Settling regime is free settling and the hindered settling. We have flow regimes, two flow regimes. When the Reynolds number is less than or equal to 1, it is called Stokes regime, right? Stokes regime. And one is Newton's regime if the Reynolds number is greater than 1000. as you can see here, greater than 1000 and less than 200,000 or 2 lakh. Okay. Okay, so why do you need Reynolds number? Reynolds number is needed to calculate the drag coefficient, right? So as you can see in this formula, you know everything, right? You know diameter of the particle, diameter of the particle, density of the particle is given, density of fluid is given, gravitational acceleration, you only don't know CD, right? How to calculate the drag coefficient. So first you have to know the Reynolds number. So if you know the Reynolds number, you can easily calculate the drag coefficient, right? So how to calculate? So we have two flow regions, right? If the Reynolds number is less than 1, then the Stokes region, so we already discussed, the drag coefficient is given by this. We already derived it in the previous lectures. So this is how it is given. So calculate the Reynolds number, then you can calculate the drag coefficient, right? And you can calculate the drag force also. Ignore GC, right? Using this formula, right? So you can calculate the terminal velocity then, because this is the terminal velocity for Stokes regime. Okay. Suppose the Reynolds number is very high. It's, let's say, higher than 1000. Okay. Greater than 1000. Then you have to calculate CD is equal to 0.4. But the CD is the drag coefficient is constant for very high Reynolds number, for greater than 1000 Reynolds number. Right? So, and the drag force is given by this. Okay. Ignore GC. And the terminal velocity is given by this. Okay. So you can check here. Okay. So what about if the Reynolds number is greater than 1, but it is less than 1000? Then we have a transition region. So we, in this region, you have to do trial and error to calculate the drag coefficient. So we'll solve the example, you'll know. Okay, so in general, you can see from above formulas that the terminal velocity varies with square, right? If it is Stokes region, so terminal velocity is directly proportional to the dp square for Stokes regime. And for Newton's law regime, we have, for Newton's law regime, this is directly proportional to the 0.5 square root. You can say square root of this. So remember this is very important. Okay. Now, instead of calculating Reynolds number to see which flow regime is in there, so you can also calculate constant K, right? So you can calculate the K like this. So based on the K value, you can directly say which flow regime is there, whether it's Stokes regime or Newton's regime. So it will be easier. So Reynolds number is this, and you put the terminal velocity formula from that. Okay, from previous Stokes law. We are talking about Stokes law. Okay, so calculate Stokes law. So you just put the terminal velocity from this equation, right? Then you will get this K is equal to this. Now to calculate the value of K, the Reynolds number is 1, right? The lower range, or you can say higher maximum value of Reynolds number for Stokes flow is 1. So how to calculate the value of K? So if K is defined like this, so what will be the relation of K with the Reynolds number, right? So you can see if you put that here, so you get the relation between Reynolds number and the K value for the Stokes regime. Okay, we are talking about Stokes regime. So this is the relation. So you know the in Stokes regime the Reynolds value is 1. So put 1 in the value of Reynolds number. So you get K, right? You just calculate the K from this equation. So you will get K is equal to 18, cube root of 18 value, and you will get K 2.6. That means if K is equal to 2.6, then it is Stokes regime, or less than 2.6, it is Stokes regime. However, if the K value is greater than 2.6, then it is not Stokes regime. Okay, neither it is Newton's law regime, because you have to check, right, what is the range of K value for Newton's law regime. So again, let's find out the K value for the Newton's regime. So in Newton's law regime, what is the terminal velocity given as? So you can check for Newton's law regime. This is the terminal velocity, right? So you can put this terminal velocity here instead of ut. So use this now. You will get the Reynolds number in terms of these values, and K is already defined like this. So try to rearrange, try to find a relation between K and this Reynolds number. Once you put the terminal velocity for Newton's law regime here, so what will be the relation you get? You will get the relation between K and Reynolds number for Newton's law regime like this. So 1.75 into K raised to the power 1.5. Now I want to find the minimum value of K, right? So because for Newton's law regime, what is the starting value of Reynolds number? That is 1000, right? It starts from 1000, then ends with somewhere 2 lakhs, right? So I want to find the minimum value of the K. So minimum value of Reynolds number is 1000 for the Newton's law regime. Just put that value in here, right, in this side, left hand side. Then we can recalculate the K value, right? So you will get K is equal to 68.9. Now, if the K value is equal to 68.9, then that means it is in the particle is in the Newton's law regime. Okay, and if it is less than 68.9, then no Newton's law, nor it is Stokes law, okay, or Stokes regime. So you have to check if the K value is 68.9 exactly or very close, then you can assume it is Newton's law regime. If it is greater than 68.9 also, then it is Newton's law regime. However, if the K value is between, if K is greater than 1 and less than 68.9, then this is neither Stokes regime or Newton's law regime. This is transition regime. So in this case, you have to do trial and error to calculate the drag coefficient. Okay, so we'll see in a while. Okay. So let's check this problem. Sorry, drag here. Okay, so if you see this problem, estimate the terminal velocity for 80 to 100 mesh particle of limestone. Density is given. Falling in water, fluid is given, water at temperature 30 degrees Celsius. How much higher would the velocity be in a centrifugal separator? So it is the centrifugal field. You have to use the centrifugal equation. So with the acceleration of 50 g. So what is the acceleration due to centrifugal force? That is AE is equal to 50 into g. G is nothing but acceleration due to gravity. Okay. So So particle size, now to find the particle size, so it is saying that it is from between 80 to 100 mesh, right? So I have to find the average between these two diameters. So if you see the appendix 20 of this book, for this 80 mesh, the diameter is given as 0.147 millimeter. And for 100 mesh, the GP is, for 80 mesh, it is 0.175. And for 100 mesh, it is 0.147. So if you take the average, as you also know, the higher the mesh number, it is the smaller, right? Smaller the diameter of the. Okay, so average diameter, just take the average. So this is the diameter. So this is the diameter of the particle. Okay. Now, what is the density of the particle? It is given. Okay. Let's calculate the fluid properties. So fluid is water, right? So what is the density of water? Now you have to calculate from appendix 14, right? So that is the significance of this temperature, right? So if the temperature is given, so you have to calculate the properties of the fluid at that temperature. So at 30 degrees Celsius, what is the density of the water? You can find from the appendix 14. So and also the viscosity, find the viscosity at 30 degrees Celsius from appendix 14. You will get this. Right, so this is the density of the water at 30 degrees Celsius. This is the viscosity of water. Right, so okay, don't confuse it this centipoise. You know the centipoise. Centi means 10 to the power minus 2, and what do you mean by poise? Poise is nothing but gram per centimeter second. Now you can convert into kg per meter second also. So divide or multiply with appropriate conversion factors. Okay, so first calculate the k, right? So as you already discussed the value of k formula, right? So just put all the values here, right? Only the difference is instead of g, you have to write 50g, okay? Because acceleration is 50g. Okay, instead of g, you have to write this. Or instead of, what was the formula? Let's check. Okay, so here this was the formula, right? Diameter of the particle just calculated, density of particle, right? And viscosity. Okay, so this is just first calculate the k. I think we don't need the angular velocity here. Maybe we need while calculating something else. Okay, so let's follow. Okay, so if you calculate the k value, so you just put the diameter. So use that equation. So you will get k is equal to 4.86. Now, so what was the range? So if k value is less than 2.6 or equal to 2.6, it is Stokes regime, right? If k is greater than 68.9, it is Newton's law regime. But this 4.86 is in between these two, right? So it is neither Stokes regime nor Newton's law regime. So what will you do now? So you have to assume Reynolds number, right? So and recalculate it. So you have to do trial and error to calculate the drag coefficient. So what you can do is just assume some Reynolds number. Let's say in this case we have assumed 4.4, right? So you can assume 4 also, you can check. So let's assume 4 or just stick to this problem. So 4.4, then you can use the figure 7.6. So what was the figure? So from this figure, if the Reynolds number is 4.86, somewhere in between, right? So we can calculate the drag coefficient. Okay, so calculate the drag coefficient. So you get 7.9. Okay, somewhere around here. somewhere around here. Okay, so now CD is calculated. Now recalculate the terminal velocity. So what is the terminal velocity in centrifugal field? Right? In general, the general equation you know. So just put here all the values. Okay, you can get it here. So you will get 0.0220 meter per second. So you have calculated the terminal velocity now. Okay, then just recalculate the Reynolds number. So if you recalculate the Reynolds number, you will get 4.40. Right? It is exactly the same as you have assumed, but this is just example. So they have exactly found the value, but if you solve it, you have to guess some Reynolds number. It can be one, it can be 2 or 5, right? So first guess the 5 value, then solve it, recheck. If this is not close, then assume another value, and so on. Just do trial and error. Okay. So our the drag coefficient, the so this is the thing. To estimate the terminal velocity, it is a particle in water. So this is done. Okay, first part. That was the first part. Now, how much higher would the velocity be in a centrifugal separator where the acceleration is 50 g? So you have to recalculate the terminal velocity. Only the case is where the gravitational uh, acceleration due to gravitational field will be 50 times, right, of the g. Okay, so the external is this 50 g. So you have to use the previous equation for centrifugal field. So in this case, just calculate the k first. So how to calculate the k first? So if you see the formula, this is the k value, right? So simply put everything. dp, only the instead of g, just put 50 into g. Okay, that's it. If you put 50 instead of g, then you'll get the k value now. Okay, just put the so they have directly done shortcut, but if you are confused how they have calculated, don't worry about this. They simply put 50g in their equation. So what will be the Reynolds number? If k is this, so Reynolds number you can find from figure 7.6, right? See, so again you have to guess the Reynolds number. Right? So k value is 17.90. So just assume some value. Here they have assumed 80. So if you put the 80 from figure this one, so if the Reynolds number is 80 here, somewhere this is 100, so somewhere here, so you can easily get something 1 point something. So CD you will be having 1 point something, so 1.2. Okay, so you can now calculate the terminal velocity. Okay, so you get 0.4 meter per second. Okay. This is how it's done. If you don't know the flow regime, then you have to use the trial and error to calculate the terminal velocity. Okay, so till now we have discussed the pre-settling, where the motion of the particle is not affected by the wall or the other particles, right? But now we'll discuss the hindered settling. In hindered settling, the motion of the particle is affected by the wall or the other particles, okay? Or you can say some kind of collisions is there between other particles, okay? So how to calculate that? So if the particle is moving in a suspension, right? So it will be offered hindrance because of other particles, right? So we call, so generally in free settling we call it terminal velocity, but now we have to call it, some kind of suspension velocity. So velocity in suspension, okay, or you can say suspended velocity or something. Okay, so this is calculated like this. So us equal to ut epsilon raised to the power n. So the velocity in the suspension is equal to velocity, a terminal velocity in free settling regime into porosity or void fraction raised to the power n. Okay, so void fraction means, like, suppose how much empty spaces are here. Suppose this total volume of the container is V, and what are the empty spaces? You cannot calculate empty spaces, so total volume minus volume of particles, right? Total volume of the particles. So in this way, the void fraction can be calculated. So it will be given in the problem. Okay. So first you have to find out terminal velocity in free settling regime. Then calculate the Reynolds number. So from this figure, if you know the Reynolds number, you can calculate the value of n, right? Suppose your Reynolds number value is 10, so the value of n will be around 3.7, right? If the Reynolds number is 100, then the n value will be 3, and so on. Okay. Also, to calculate the terminal velocity, first you have to calculate the k value, right? K criteria. If the k is the Stokes in the Stokes flow regime, then use the appropriate terminal velocity equation. And if the k is in the Newton's law regime, then use that ut equation. And if this the k value is in between these two regimes, that is Stokes law and the Newton's law regime, then you have to use trial and error as shown in the previous example. Okay, so how to, let's solve a problem. You'll get a clear idea how to solve, or how to find the suspended velocity or velocity in the suspension. So if you see this problem, it is straightforward. So particles of sphelerite, sphelerite is something, some ore. Specific gravity is given, right? As specific gravity are settling under the force of gravity. So external force is gravitational force in carbon tetrachloride. So the fluid in which the particle is settling is carbon tetrachloride, not water. At 20 degrees Celsius, temperature is given, and the specific gravity of this carbon tetrachloride is this. So what will be the density? Yeah, density. I think you have to multiply with the density of water at this temperature, right? So the diameter of the spheroid particle is given, right? 10 millimeter or 0.004 inch. The volume fraction of the spheroid in, so epsilon is given as 0.20. What is the settling velocity of the particle? So spheroid. Okay. So this is no more terminal velocity, but we call it settling velocity now. Okay. So you can see us. So it is called settling velocity or velocity in the suspension. Now, so first you have to calculate the terminal velocity, right? So to calculate, because it is this formula, right? So first you have to calculate the terminal velocity. But to calculate terminal velocity, you have to know the flow regime. You have to first calculate the value of k. So first calculate the value of k, right? So you know dp. So if you see dp is 0.004 inch, but it is divided by 12 to make it in feet. Because if you see the calculations, everything is done in British units. Okay. British units or pound system, FPS system, right? Foot pound second. So you can do in SI units also, it's your choice. So if you want to follow through this example, then follow the same units. Okay, so just find the value of k. Then it is found that the value of k is 3.34, right? So the if the value is of k is 3.34, what is the flow regime? So for Stokes flow, it was around 2.6, and if it is Newton's regime, it was 68.9, something like that, right? So you can check it. So if you can see, the k value is almost close to 2.6, right? So if it is almost close to the Stokes flow regime, then you can use the terminal velocity formula for the Stokes regime, right? So use that and find out the terminal velocity. So it is found to be like this. Okay, if this k value was very higher, like 10 the k, then you cannot assume that this is Stokes flow regime. So you have to do trial and error as in previous example. Okay, so now this is close to 2.6, so you can assume it is Stokes flow. Then use the appropriate equation, so you can calculate the terminal velocity. Okay, so you know this now, terminal velocity, because you want to calculate the settling velocity in the suspension. So you also know the for volume fraction, right? So that is 0.20. Only you don't know is n value. As I told you, to calculate the n, first you have to calculate the Reynolds number. So first calculate the Reynolds number. So if you calculate the Reynolds number, then it is found to be 2.06, right? So if the Reynolds number is 2.06, then what will be the value of n? So from this figure, you can see what is the value of Reynolds number? 2.2. You can assume 2. So this is 2, right? So what is the value of 2? It's around 4.1, right? So the n is found to be 4.1 from the graph. Okay. Now you can calculate the suspended velocity or the settling velocity in the suspension, right? So you can see here, this is how you find the settling velocity in hindered settling mode. Okay, see you in the next class. Thank you.